This from the Eastern Cape, 2020 September. Question 8. In an experiment to determine the EMF and the internal resistance of a battery, a group of learners connected the circuit diagram below. They recorded the ammeter and the voltmeter readings. They repeated the experiment each time with different resistance. So we have that diagram, and then we have a graph of the inverse of current versus the resistance. What is the independent variable for this experiment? So the independent variable is something that you change during the experiment. So in this instance, we are using different resistance. So that will be the independent variable. So resistance will be the independent variable. Another way you can look at it, whenever you have a graph like this one, whatever is on the x-axis, that will be your independent variable. 8.2. Using the equation that 8.21, calculate the EMF of the battery. So we are given 1 over I equals to R plus R all over the EMF. Let's rearrange this. So this should be 1 all over the EMF multiplied by resistance plus 1 over the EMF multiplied by R. So these two are exactly the same thing. Now we have Y is equals to mx plus C. So the inverse of the current is what you have on the y-axis. So this is 1 over I. The gradient should be the inverse of the EMF. And then what you have on your x-axis is the resistance. And then the y-intercept should be the inverse of the EMF multiplied by the internal resistance. So here they are looking for the EMF. So the gradient should be equals to the inverse of the EMF. So this is change in 1 over I all over change in resistance. We'll choose any 2 points on the graph. So I'm going to pick the 10, and the 10 is going to go with that point right there. So this is 2, 4, 6, 8, 10, okay, 2, 4, 6, 8, 10, yeah. So that is a 1.8. So that's 1.8 minus. So I know that when the inverse of the current is 1.8, the resistance should be equals to 10. Then I'm going to pick another point. I'm going to pick 5, and then that point right there. So it's 1.0 minus a 5. So I'm getting 0.16. But don't forget that this is the inverse of the EMF. So in order to get the EMF, I need to find the inverse of that. So I'm getting 6.25 volts. The internal resistance of the battery. Okay. You remember we said the y-intercept should be equals to this whole thing. And then Right here, we do have the y-intercept at that point, and that is 0.2. So 0.2 should be equals to 1 all over the EMF multiplied by the internal resistance. 0.2 should be equals to 1 over 6.25 multiplied by the internal resistance. So I'm getting 1.25 ohms. Another way that you can find the internal resistance, you can say the EMF should be equals to the current multiplied by R plus the internal resistance. So you know that the EMF is 6.25. That right there should be the inverse of the current. So you just pick any point. So this is 1 over I, which is equals to, we're just going to choose any point. Let's pick 15. So the 15 is going to be there. So it goes with that point right there. So 2.2, 2.4, 2.6. So that's a 2.6. Therefore, I should be equals to the inverse of that. So I'm getting 5 over 13. So I'm just going to substitute 5 over 13 there. And the resistance at that point should be 15. 6.25 divided by 5 over 13. So this is 65 over 4, which is equals to 15 plus the internal resistance. So I'm getting 1.25 ohms. So it works as well. 8.3. In the circuit diagram below, the battery used in the above experiment is connected to 3 resistors and a toy car that is rated 3 watts. So this is 3 watts, and then the potential difference is 1.5 volts. We are still using the same battery. The EMF of a battery doesn't change. So the EMF will still be 6.25 volts, and the internal resistance doesn't change as well. So this is going to 1.25 ohms. Let us analyze the circuit. So we will look for the longer terminal of the battery. In this instance, this is the longer terminal. So those two are the longer terminals. So the total current should flow from the positive part of the battery to the negative. So which means the total current would flow this way. That is I total. At the junction right there, the current should be divided. So we will have I1, and then in this direction we will have I2. For resistors connected in series, they are potential dividers, but the current remains the same. So we will still have that same I1 flowing through these two resistors. On the other part of the junction, this will be the I total. So at this point right here, I1 and I2 will combine again to form I total. The current that will be passing through the ammeter will be the I total. And then the current will go back inside of the battery. 8.3.1. When the switch S is closed, calculate the reading on the ammeter So we are given the power as well as the voltage. We will use this formula. Power should be equals to the voltage multiplied by the current. The power is 3 and the voltage is 1.5. Therefore, I should be equals to 2. So this is 2 amperes. 8.3.2. We need to find the resistance of R, that R there. So the first thing we need to find is the R external, because we don't know what the total resistance is. Since we have the EMF and the internal resistance together with the total current, we will use this formula. We use this formula when we have the totals. So this will be the total current, and then this will be the total external resistance. 6.25 should be equals to 2.0 R external plus 1.25. Therefore, R external should be equals to, so I am getting 1.875 ohms. Now let's look at the circuit. So we have so these are all the resistors that we have. And then this is the resistor of the toy. We will start with these two. So that is they're in series, so that will be the series combination. And for resistors connected in series, we just add the resistors. So this is 3 ohms. Okay, now our circuit will look like this. So this is 3 ohms, that's R, and that's the R of the toy. And then we'll find the parallel combination, because the 3 ohm resistor is connected in parallel to the R resistor. So R parallel should be equals to, we take the first resistor, we multiply it with the second one, and then we just find the sum of the two. That is the parallel combination. Now our circuit will look like this. So now we have R parallel together with the R of the toy. But we don't know what the R of the toy is, but we can find it because we have the power, we have the potential difference as well. The power should be equals to 3. The potential difference is 1.5 R. The resistance of the toy is therefore so I'm getting 0.75 ohms. These two are connected in series, so we'll just add both of them. So R external should be equals to the parallel combination plus the resistance of the toy. R parallel should be equals to 3R all over 3 plus R. The resistance of the toy is 0.75. But R external is 1.875. We've calculated it. So here I'm getting 1.125 3R all over 3 plus R. So this is 3.375 plus 1.125 R. Therefore, R should be equals to 3.375 all over 3 minus 1.125. So I am getting 1.8 ohms. 8.4. If the resistor R is removed from the circuit, will the toy car be able to operate as rated? Answer only yes or no, and then explain your answer. Well, should the total current decrease, the toy will not be able to operate as rated, because currently we are using 2.0 amperes of current in order for the toy to operate as rated. If the total current in the external circuits decreases, then the toy will not be able to function. So let's take a look at what's happening there. So we are killing that R there. So whenever you remove a resistor from a parallel combination, the effective resistance of the circuit will increase. So R external increases. That's the first thing that we look at. It means that the current should decrease. If the current of the circuit decreases, then the toy will not be able to operate.